Hi everyone, welcome to GemChem. Now today's video is on heterocyclic compound part 3 video, and here we are going to deal with synthesis of Pyrrole. Now before starting, already two videos are uploaded in channel, you can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now once we complete the synthesis of Pyrrole, we are going to deal with the structure of thiophene and furan and continue with its synthesis. At first, we are going to deal with the different methods or the back pathways, that is retrosynthetic pathways for Pyrrole synthesis. And in the first case, we are going to try to break the bond to get a 4-substituted Pyrrole, and the breaking of bond can take place between the carbon and nitrogen bonds. So once we try to break it, our synthones can be this one. So we can see here, this can break to give us diketone, and 1,4-diketone is my substrate along with ammonia or any kind of amine. This synthesis is known as Paal-Knorr synthesis. Next, another method is that we can have 4-substituted Pyrrole, and in that case the disconnection approach will be something different. So we are trying to disconnect from here and from here as well as from here. So in that case, the substrate comes to be as this part, we have a chloro part and these two are diketone. And when we talk about the NH3 and RNH2, which is present to react with the two ketones present in the two different substrate. This type of synthesis is known as Hans synthesis. And another one which we are going to talk about is when the disconnection approach starts from here and here, we get two substrate, that is this one. So we have a NH2 and a ketone this side, and here we have only one ketone. So this synthesis is known as Knorr synthesis. After this, we can have this type of Pyrrole ring where CO2R is present, and this can be done using another different substrate where breaking of bond takes place in the double bond section. And the substrate which can be used, or the synthone which can be used, are this one where we have a NO2 group around an alkene and we have a cyanide. This type of synthesis is known as Barton-Zard synthesis. And last one, in which we have only CO2R, in that case we can disconnect the bond between this part and this part. So our substrate can be double bond and a ketone as well as NHR CO2R. Now from here only we are going to concentrate with one particular synthesis, that is Paal-Knorr synthesis. And this synthesis is done using 1,4-dicarbonyl compounds. So what is the disconnection approach? We are going to see that always carbon-nitrogen bond breaks easily and its formation is also easy. So we may consider the disconnection approach as follows, that is, we are going to break the carbon-nitrogen bond. Once we have broken the carbon-nitrogen bond, the component which we are getting is this one, carbon chain as well as nitrogen. Now we always know that nitrogen has lone pair in it. As a result, it can act as nucleophile. The synthones can be separated by using charge separation, and we can denote it like this. So you can see here, since nitrogen is negatively charged, 2 electrons, these carbons can be tagged as positively charged. And the best way to provide carbon with a positive charge is to provide it with a ketone group. As a result, our final synthones comes to be as this diketone, 1,4-diketone, and any kind of amine or ammonia. So now we are going to try to see one of the reaction where there is formation of Pyrrole, and when the Pyrrole is being formed, it is substituted in 2 and 5 position. So we are going to see the synthesis of 2,5-dimethyl 1H Pyrrole. And this one is our hexane 2,5-dione. So once this takes place, the reaction is like the NH2 which is present here, ammonia as a lone pair tries to attack this one, this opens up and takes up a hydrogen. So here we have NH2OH. Now this OH has a lone pair. It abstracts the proton from here. This hydrogen gives away the bond to this carbon-carbon, as a result of which OH2 plus, being a good leaving group, comes out. So we get this type of substrate. Again the same reaction takes place, and there the nitrogen here in this case has lone pair. So it will attack this position. This will open up, OH formation. Again after OH formation, OH will obstruct the proton from this part. H will give away the bond and OH will come out. Finally, the product which is obtained is our 2,5-dimethyl-1H pyrrole. But one of the important question is where to get the starting material. So for this case, we are going to see how this one synthesized. So here you can see the synthetic pathway. We have taken this such kind of molecule. Once we have taken this one, this center is going to act as carbon for the pyrrole ring. Sodium diether takes away the hydrogen present here. As a result, this part gains a negative charge. Once this gains a negative charge, in presence of iodine, they couple together, because this one will attack another molecule of same type. As a result, we get this molecule. Once this is done, we add 20% aqueous K2CO3 to remove this part. Thus, these two parts get removed and we get our hexane 2,5-dione. Now remember, in Paal-Knorr synthesis, it is excellent method, but limitation is that the availability of diketone is absolute necessity. And here dehydration takes place, but no dehydrogenation step is necessary. Now we are going to try to synthesize unsubstituted pyrrole. And in this case, we are going to use 2,5-dimethoxy tetrahydrofuran as a succinaldehyde equivalent, and this expands the Paal-Knorr synthesis to include unsubstituted pyrrole. So this is the synthesis where you can see that this is 2,5-dimethoxy tetrahydrofuran, where we have added RNH2 in presence of P2O5 to obtain this part. Now R can be considered as methyl, butyl, benzyl, phenyl, aryl, CH2COMe, tosyl, as well as COCH2 CH3. So many groups are possible to get substituted in NR. Another method can be a useful synthesis of N-alkyl pyrroles, where distillation or the dry distillation of alkyl ammonium salt of mucic acid or saccharic acid is used. Probably also proceeds by the 1,4-dicarbonyl intermediate which we are talking about, and we already know that pyrrole carboxylic acids are easily decarboxylated, because we have already seen the retrosynthetic pathways where we have seen CO2R can be easily generated. So remember, pyrrole carboxylic acids are easily decarboxylated. So this is the approach. See here, we have taken this molecule and you can see in this part you have CO2H. Now on dry distillation, what happens is that this part OH and this part OH is being lost along with the hydrogen present, as a result of which here we get a diketone. Now on losing 2 carbon dioxide as well as 2 water, we get N-butyl pyrrole, and in this case 2 moles of CO2 and 2 moles of water is being lost, and the reagent which is added is tertiary butyl NH2. We can have an intermediate like this, where we have a pyrrole ring and this is being formed, pyrrole with tertiary butyl group, and we have a CO2H and CO2H, which is decarboxylated, and here it is 2CO2. So this can be one of the intermediate step. Now we are going to see how to synthesize this particular pyrrole ring. Now always remember, when the pyrrole has in the second position ketone, then usually ester is taken as the substrate. So first, same way we are going to follow the disconnection approach, that is this part. These two will be disconnected. Once these two disconnects, we are going to write down the synthone present. So this one will be this same thing, here double bond, here will be hydrogen. Here, since I have told you that there will be an ester group, so this will be COO, CH2, CH3. This part will remain same, COO, CH2, CH3, and here going to have same number of hydrogens as present. Now since this part is one of the synthone, as you can see here, the disconnection for formation of this part is like this. And another synthone which is present here along with this one is your ammonia for this portion. Now we are going to find out the next position. That is, we have COO, CH2, CH3, and this one COO, CH2, CH3. Take for this part, this particular molecule, H, C double bond O, CH2, CH3. So from here we can easily extract this part, right? So HC double bond O will be obtained from this moiety. Now let us try to see the whole total synthetic pathway. So first we have taken the molecule, then to it we have added sodium hydride and HCOO, CH2, CH3. What happens is the aldehyde portion of one carbon gets included here. Once it is done, we are going to add NH3 to it. So here the NH3 becomes NH2, and the hydrogen which was present in this position gives away, and OH2 plus moves out from the carbon. As a result, NH2 comes here. Now we have provided with KOCH3 whole thrice benzene. Once we have provided this one, this goes out while NH2 bonds with this portion and the ketone remains as it is. This one helps us to produce what we desired for, and further if other molecules are asked for, if you add to this one NaOH followed by heating, then H3O plus, and heat it with powdered glass, you are going to get this molecule, where your ester group which was present in the fourth position gets removed. So this comes like this. Okay. And another method is that you can convert this position into a ester part by adding acetyl anhydride. So once you add acetyl anhydride, that is number 1, you are going to add CH3 CO 2O and sulfuric acid H2 SO4. So you are going to get NH, and in this position you will have OCO CH3, and here you are going to have COO CH2 CH3, right? So for this particular molecule, this part I am going to take as R and not carry forward it together. So if we consider here the retrosynthetic pathway, we are going to break this bond as well as this bond, and in the same way as that previous one, we are going to have the moiety as this part having cyanide. I have told you already that this part you are going to take as cyanide only. This part is again CHO group. So once you continue this connection, this part will be NH2 and the R group whole as it is. Once you try to disconnect this one also in the same way as that of the previous one, so try to disconnect this part, you are going to get the synthone CH2. Here you have CN, CH2, CN along with HCOO, CH3, CH2, CH3. Right? Now from where do we get this one? If we try to get in the back position, this one will come from CONH2 and this one also CONH2. If we talk about this synthone particularly, this can be obtained by using Cl, CH2, CH2, CH, O, ET whole twice, and this can be again obtained from CH2 double bond CH, CHO, and if we again try to break down, we will have alcohol in the three positions, that is CH2, OH. Similarly, here we will have CH, OH, and here we are going to have CH2, OH. So these are the previous synthones, but we are going to start our synthesis from this one and this one. No further breaking down of the starting material. Okay. So let us see the synthesis in details. So we have the cyanide moiety. We are going to react the cyanide moiety in the same way as the previous one to introduce CHO group. So we have taken HCOO, CH2CH3, and in presence of NaH it is added along with H3O plus. We get this portion. Once we get this portion, we are going to add our previous substrate NH2, CH2, CH2, CH, OCH2, CH3 whole twice. Once we add this gets added up in this portion with nitrogen, and now finally when we add NaOCH2, CH3 and ethanol and heat it, these two fuse together and this becomes NH2. So we have obtained our substrate, and from the substrate we have obtained our product. The last part which we are going to deal with is the application of Paal-Knorr synthesis. Now generally we have seen right now that NH2 is getting trapped within a ring. So from here we can conclude that this Paal-Knorr synthesis can be very useful as a method to protect the primary amine, and one of the method is being shown here. So if you see here, a resorcinol is being taken and it is reacted with hydrogen nickel. So it is basically converted into diketone. Once it is converted into diketone, to it we have added NaOCH2CH3 and BrCH2COCH3. Once we add this CH2COCH3 gets attached to this portion. NaOCH2CH3 causes the loss of proton from here. Once it loses the proton, this gets attached with the CH2COCH3. So we have now obtained 1,4-diketone. Now if my target molecule is RNH2, which must be protected, we are now going to add RNH2 in it, and thus you can see here pyrrole ring formation and this RNH2 gets protected. So here ends the topic of Paal-Knorr synthesis. Hope I have made the most out of it. And another one is that try to synthesize this particular molecule and see to it if you can do it or not. So this is your target one. Here you have nitrogen and a pyrrole ring. So CH2, CH2, N, and you have this again another pyrrole ring. So this is your checkpoint. You need to synthesize this one. So here ends the topic of Paal-Knorr synthesis. In the next video, we are going to deal with Knorr synthesis. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.